Hi everyone, we're going to do some examples with acids and bases in this video, but the key to solving these problems is recognizing the solute. Is the solute HA? If it's HA, then it's a weak acid problem and you would use Ka. Here's some example solutes that you would think of as HA. Acetic, nitrous, hydrogen cyanide, HF. I think this is butanoic acid or hypochlorous acid. All of these solutes are weak acid and you would use a Ka to solve this problem. I would start with quick and dirty. H plus equals the square root of Ka times the formal concentration of Ha. On the other hand, if your solute is A minus, for example, these solutes, these are all the conjugate bases, then it would be a Kb problem. I again would use OH equal to the square root of Kb times the formal concentration of A minus. This is the key. If you don't know that you have HA or A minus, the problem is going to be wrong. Notice in this example that I've given you here, all of these weak acids are neutral and all of these weak bases have a negative charge. But that isn't the case for solutes that contain nitrogen. Acids could be also thought of as BH+, and here are some examples. Ammonium, ethylammonium, dimethylammonium. These are also weak acid problems. You would use H plus is equal to the square root of Ka times the formal concentration of that solute, which is BH plus. So always go back to the simplest example, which is ammonium. Nitrogen with 4 bonds attached to it is going to have a positive charge and is going to be BH plus or a weak acid. If you look closely, all of these nitrogens have 4 bonds, and that's why they all have a positive charge. B, these solutes are all neutral, and these are examples: ammonia, ethylamine, dimethylamine. These are all weak bases, and you would use Kb. You would use this quick and dirty equation, Kb times the formal concentration of the base. Always go back to the simplest example of ammonia. Ammonia has 3 bonds to it, and it has this lone pair where it can accept a proton from water. If you look at these other examples, these nitrogens have 3 bonds, just like ammonia, making them weak bases. So let's see if we can figure some of these out. Our first example is potassium benzoate, and this is the information that Harris gives you in the appendix, and this is the information that I'm going to give you. Remember, you're given the name of the neutral compound, the structure of the fully protonated form, and the pKa and the Ka. So I don't know how you see this problem, but when I first see this, I see potassium that has a plus charge. Benzoate has to have a negative charge. It's got to be A minus. Or maybe another way to think of this is, well, if we're given the name of the neutral compound, this is not the same name. It's got to be A minus. So the pH of A minus behaves as a weak base to form HA and OH. At equilibrium, we would have 0.052 formal minus X, X for HA, X for OH, but I'm going to just try to do quick and dirty. OH is going to be equal to the square root of KB. Well, I don't know KB. KB will be KW over KA. Let me solve for that. I'm getting 1.5 with an insignificant 9 times 10 to the negative 10th. So now I can plug that here for Kb times that formal concentration. And let's see what we get. I'm getting 2.8 with an insignificant 8 times 10 to the negative 6 molar OH. And let's just make sure that that is less than 1%. Oh yeah, that's much less than 1% of that formal concentration of A minus. So taking the pH, I got 8.46 as the pH. And there are a couple of different ways that you can get the pH from the hydroxide concentration. Maybe we'll talk about those in class. Let's try to do another example. The pH of 0.1 formal ethylammonium chloride. Again, this is the information that Harris gives you, so this is the information that I'm going to give you. The key to solving this problem is it HA, A minus, is it BH plus, or B? So when I look at this, I'm thinking that chloride is negative, so the counter ion must be positive, meaning that it must be BH plus, which is a weak acid. So just to be clear, BH plus is going to be in equilibrium with H plus, and B at equilibrium, we would have 0.10 formal minus X, X for H plus, and X for B. But I'm going to go ahead and try quick and dirty. H plus equals the square root of Ka. Well, they gave it to us. That's 3.18 times 10 to the negative 10th. The formal concentration is 0.10 formal. And let's see what the arithmetic gives us. I'm getting 5.6 with an insignificant 4 times 10 to the negative 6 molar for H plus. And let's make sure that that's less than 1% of 0.1 formal. Oh yeah, it is. So just take the negative log of that number and you'll get a pH of 5.24 with an insignificant 9. So we thought we had a weak acid, we got an acidic pH. Things are making sense. Let's try another one. So we've got sodium formate. Again, this is the information that Harris will give you in the appendix. And when I think of sodium, I know it has a positive charge. That must mean formate is a minus. So again, out of all of our options, HA, A minus, BH plus, or B, A minus is the only one that makes sense. So I'm going to be brave here and just write down quick and dirty. OH equals the square root of Kb times the formal concentration of A minus. Kb we have to solve for. And we have to solve for Kb by taking Kw over Ka. I got 5.5 with an insignificant 6 times 10 to the negative 11th. The formal concentration is 0.034 formal. And let's see what we get. I'm getting 1.3 with an insignificant 7 times 10 to the negative 6th molar OH. And let's make sure that that's less than 1% of this formal concentration. Yes, it is. So now, using OH to find the pH, I am getting 8.14. So we thought we had a weak base. We got a basic pH. Again, I think things are working out for us. And can we find the pH of ammonia? Again, this is the information you'll be given. So now the decision to make, as always, is do we have HA or A minus, or is it BH plus or B? Now, you have to know that the formula for ammonia is NH3. And remember, Harris always gives you the name of the neutral form and the structure of the fully protonated form. So we do have the neutral form. This is a weak base problem. So I'm just going to go ahead and try to use quick and dirty. That's the square root of Kb. Well, we have to work to get Kb. And I got 1.7 with an insignificant 6 times 10 to the negative fifth times the formal concentration, which is 0.1. So I'm getting an OH concentration of 0.0013 with an insignificant 3 molar OH, and I better make sure that that's less than 1%. Well, it's not less than 1%. This is about 1.3% of that formal concentration, but I think that's good enough for us. It's still less than 5% of that formal concentration of ammonia. So I'm just going to use this OH concentration to get the pH, and I'm getting 11.12 as the pH. And again, we thought we had a weak base. We ended up with a basic pH. Things are making sense. I'll leave you with one final example, the pH of this solute. Maybe I'll just give you the answer. You should get a pH of 4.97. If you got a pH of 5.12, you forgot that for every 1 mole of this salt, there are 2 moles of the ammonium ion. So I'll let you struggle with this one on your own, and hope you enjoy these examples. Thanks for listening. We'll do more in class.